Do you know the Project Orion, the secret spaceship propelled by nuclear bombs?
Section 51.
Section 51.
Section 51.
Hi everyone, what's up? I am GH aka DOSGeek. It's nice to be back here with you and Section 51. And thank you again for your support to the channel. One of the biggest things holding us back from exploring the universe is that it takes years to traverse the huge distances between planets. It would take close to 165,000 years to reach our closest neighboring star using the space travel technology we have today. Engineers are currently developing ion propulsion systems that will help pick up the pace. But space travel technology could have ended up on a very different path about 60 years ago. Project Orion was a study of a spacecraft intended to be directly propelled by a series of explosions of atomic bombs behind the craft, the nuclear pulse propulsion. Early versions of this vehicle were proposed to take off from the ground with significant associated nuclear fallout. Later versions were presented for use only in space. 6 tests were launched. A monstrous craft was designed as a multi-mission platform. The idea was to go to Mars in 1965, then to Saturn in 1970 with a stopover on Mars along the way. And how would it do this? By dropping atomic bombs out the stern and riding the blast waves. Orion was under very serious consideration by a US government looking to create the world's first true spaceship that, if completed, would have made Apollo look like a toy. So serious was this commitment that from 1957 to 1965, Washington spent $10.5 million, around $85 million US dollars in today's money, on the idea, with many of the same minds behind the Manhattan Project turning their expertise from creating weapons of war to developing a means of space travel. The project was so advanced that much of the work is still classified half a century later. The idea of rocket propulsion by combustion of explosive substance was first proposed by Russian explosives expert Nikolai Kibalchich in 1881, and in 1891 similar ideas were developed independently by German engineer Hermann Ganswind. General proposals of nuclear propulsion were first made by Stanislav Ulam in 1946, and preliminary calculations were made by F. Raines and Ulam in a Los Alamos memorandum dated 1947. The actual project, initiated in 1958, was led by Ted Taylor at General Atomics and physicist Freeman Dyson, who, at Taylor's request, took a year away from the Institute for Advanced Study in Princeton to work on the project. The Orion concept offered high thrust and high specific impulse or propellant efficiency at the same time. The unprecedented extreme power requirements for doing so would be met by nuclear explosions of such power relative to the vehicle's mass as to be survived only by using external detonations without attempting to contain them in internal structures. As a qualitative comparison, traditional chemical rockets such as the Saturn V that took the Apollo program to the moon produce high thrust with low specific impulse, whereas electric ion engines produce a small amount of thrust very efficiently. Orion would have offered performance greater than the most advanced conventional or nuclear rocket engines then under consideration. Supporters of Project Orion felt that it had potential for cheap interplanetary travel, but it lost political approval over concerns with fallout from its propulsion. The Orion nuclear pulse drive combines a very high exhaust velocity from 19 to 31 km by second in typical interplanetary designs with meganewtons of thrust. Many spacecraft propulsion drives can achieve one of these or the other, but nuclear pulse rockets are the only proposed technology that could potentially meet the extreme power requirements to deliver both at once. The Orion concept detonates nuclear explosions externally at a rate of power release which is beyond what nuclear reactors could survive internally with known materials and design. Since weight is no limitation, an Orion craft can be extremely robust. An unmanned craft could tolerate very large accelerations, perhaps 100 g. A human crewed Orion, however, must use some sort of damping system behind the pusher plate to smooth the near instantaneous acceleration to a level that humans can comfortably withstand, typically about 2 to 4 g. The high performance depends on the high exhaust velocity in order to maximize the rocket's force for a given mass of propellant. The velocity of the plasma debris is proportional to the square root of the change in the temperature of the nuclear fireball. Since fireballs routinely achieve 10 million degrees Celsius or more in less than a millisecond, they create very high velocities. However, a practical design must also limit the destructive radius of the fireball. The diameter of the nuclear fireball is proportional to the square root of the bomb's explosive yield. The shape of the bomb's reaction mass is critical to efficiency. A bomb with a cylinder of reaction mass expands into a flat, disc-shaped wave of plasma when it explodes. A bomb with a disc-shaped reaction mass expands into a far more efficient cigar-shaped wave of plasma debris. The smaller the bomb, the smaller each impulse will be. So the higher the rate of impulses and more than will be needed to achieve orbit. Smaller impulses also mean less G shock on the pusher plate and less need for damping to smooth out the acceleration. The optimal Orion drive bomblet yield for the human-crewed 4,000-ton reference design was calculated to be in the region of 0.15 kilotons, with approximately 800 bombs needed to orbit and a bomb rate of approximately 1 per second. The biggest design is the Super Orion design, at 8 million tons. It could easily be a city. In interviews, the designers contemplated a large ship as possible interstellar ark. This extreme design could be built with materials and techniques that could be obtained in 1958 or were anticipated to be available shortly after. Most of the 3,000 tons of each of the Super Orion's propulsion units would be inert materials such as polyethylene or boron salts used to transmit the force of the propulsion unit's detonation to the Orion's pusher plate and absorb neutrons to minimize fallout. The Orion nuclear pulse rocket design has extremely high performance. Orion nuclear pulse rockets using nuclear fission type pulse units were originally intended for use on interplanetary space flights. Missions that were designed for an Orion vehicle in the original project included single stage directly from Earth's surface to Mars and back, and a trip to one of the moons of Saturn. Freeman Dyson performed the first analysis of what kinds of Orion missions were possible to reach Alpha Centauri, the nearest star system to the Sun. His 1968 paper, Interstellar Transport, in Physics Today, of October 1968, retained the concept of large nuclear explosions, but Dyson moved away from the use of fission bombs and considered the use of 1 megaton deuterium fusion explosions instead. To estimate the upper and lower limits of what could be done using contemporary technology, in 1968, Dyson considered two Starship designs. The more conservative energy-limited pressure plate design simply had to absorb all the thermal energy of each impinging explosion, half of which would be absorbed by the pressure plate without melting. Dyson estimated that if the exposed surface consisted of copper with a thickness of 1 mm, then the diameter and mass of the hemispherical pressure plate would have to be 20 kilometers and 5 million tons, respectively. 100 seconds would be required to allow the copper to radiatively cool before the next explosion. It would then take on the order of 1,000 years for the energy-limited heat-sink Orion design to reach Alpha Centauri. Later studies indicated that the top cruise velocity that can theoretically be achieved are a few percent of the speed of light. An atomic fission Orion can achieve perhaps 9% or 11% of the speed of light. A nuclear pulse drive Starship powered by fusion antimatter catalyzed nuclear pulse propulsion units would be similarly in the 10% range, and pure matter-antimatter annihilation rockets would be theoretically capable of obtaining a velocity between 50% to 80% of the speed of light. In each case, saving fuel for slowing down halves the maximum speed. The concept of using a magnetic sail to decelerate the spacecraft as it approaches its destination has been discussed as an alternative to using propellant. This would allow the ship to travel near the maximum theoretical velocity. At 0.1 c, where c is the speed of light, around 300,000 km per second, Orion thermonuclear starships would require a flight time of at least 44 years to reach Alpha Centauri, not counting time needed to reach that speed, about 36 days at constant acceleration of 1 g. At 0.1 c, an Orion starship would require 100 years to travel 10 light-years. The astronomer Carl Sagan suggested that this would be an excellent use for current stockpiles of nuclear weapons. The expense of the fissionable materials required was thought to be high until the physicist Ted Taylor showed that with the right designs for explosives, the amount of fissionables used on launch was close to constant for every size of Orion, from 2,000 tons to 8 million tons. The larger bombs used more explosives to super compress the fissionables, increasing efficiency. The extra debris from the explosives also serves as additional propulsion mass. The bulk of costs for historical nuclear defense programs have been for delivery and support systems, rather than for production cost of the bombs directly, with warheads being 7% of the US 1946 to 1996 expense total, according to one study. After initial infrastructure development and investment, the marginal cost of additional nuclear bombs in mass production can be relatively low. In the 1980s, some US thermonuclear warheads had $1.1 million estimated cost, each around $630 million for 560. For the perhaps simpler fission pulse units to be used by one Orion design, a 1964 source estimated a cost of $40,000 or less each in mass production, which would be up to approximately $0.3 million each in modern-day dollars adjusted for inflation. Project Daedalus later proposed fusion explosives, deuterium or tritium pellets, detonated by electron beam inertial confinement. This is the same principle behind inertial confinement fusion. Theoretically, it could be scaled down to far smaller explosions and require small shock absorbers. From 1957 to 1964, the world's vehicle architecture was used to design a spacecraft propulsion system called Orion, in which nuclear explosives would be thrown behind a pusher plate mounted on the bottom of a spacecraft and exploded. The shock wave and radiation from the detonation would impact against the underside of the pusher plate, giving it a powerful push. The pusher plate would be mounted on large two-stage shock absorbers that would smoothly transmit acceleration to the rest of the spacecraft. Exposure to repeated nuclear blasts raises the problem of ablation or erosion of the pusher plate. Calculations and experiments indicated that a steel pusher plate would ablate less than 1 mm if unprotected. If sprayed with an oil, it would not ablate at all. This was discovered by accident. A test plate had oily fingerprints on it, and the fingerprints suffered no ablation. The crew module on the Orion was nothing like what was as flown even today. The multi-deck module was not only spacious and well appointed with multiple gangways, control rooms and crew quarters, but it was also protected against cosmic radiation by thick hydrogenous shielding, and there was even a bunker in case of solar flares and the like. Even more impressive, the whole ship rotated when not accelerating, so the crew could enjoy artificial gravity. There were landing craft, which were only penciled in but resembled the space shuttle, a pair of space taxis, and the entire module had its own rocket system, so it could act as a lifeboat. But the main unsolved problem for a launch from the surface of the Earth was thought to be nuclear fallout. Freeman Dyson, group leader on the project, estimated back in the 1960s that with conventional nuclear weapons, each launch would statistically cause on average between 0.1 and 1 fatal cancers from the fallout. The original idea was to use a bomb to raise Orion off its launch pad, but this was discarded due to a huge cloud of radioactive dust that would be thrown into the atmosphere. It was therefore decided to rest Orion on a giant ring of conventional explosives to throw it into the air. Once aloft, the atomic bombs would take over. Detonating in mid-air, there would much less fallout. But danger to human life was not a reason given for shelving the project. Bear in mind that this isn't a direct causal relationship, but a statistical probability based on the no-threshold hypothesis. Dyson felt that while the probability of one death was acceptable, 10 was out of bounds. At the same time, Taylor believed that special bomb designs could reduce the fallout hazard by a factor of 10 or even eliminate it if a pure fusion explosion could be produced. The main threats to the project included lack of emission requirement, the fact that no one in the US government could think of any reason to put thousands of tons of payload into orbit, the decision to focus on rockets for the moon mission, and ultimately the signing of the Partial Test Ban Treaty in 1963. The danger to electronic systems on the ground from electromagnetic pulse was not considered to be significant from the sub-kiloton blasts proposed, since solid-state integrated circuits were not in general use at the time. The launch of such an Orion nuclear bomb rocket from the ground or low Earth orbit would generate an electromagnetic pulse that could cause significant damage to computers and satellites, as well as flooding the Van Allen belts with high-energy radiation. Since the EMP footprint would be a few hundred miles wide, this problem might be solved by launching from very remote areas. A few relatively small space-based electrodynamic tethers could be deployed to quickly eject the energetic particles from the capture angles of the Van Allen belts. Without atomic tests, there was no way to develop the spacecraft any further. Committed to the space race, the government threw its backing behind Apollo and the Saturn V, divorcing Orion from the mainstream space program. Meanwhile, the Air Force was stuck with a non-military project that, by law, they couldn't back. As Orion became more scientifically feasible, it became less palatable, and by late 1963, the only interest came from the Strategic Air Command, which was intrigued by the idea of a deep space fleet. Ironically, one of the biggest nails in Orion's coffin was an 8-foot model the team built to show off a complete spacecraft. Long vanished, it was an impressive display of what the finished product would look in a cute way detail, but to Washington, this was less convincing than a vague proposal had been. In 1965, in one final attempt to keep Orion alive, General Atomic went to the US Atomic Energy Commission for permission to conduct underground tests. The AEC was receptive, but NASA said that this was pointless because it had no plans for manned planetary missions. Orion had no backers, no mission, and no money. On June the 30th of 1965, the Air Force officially shut the project down and 7 years of work was shelved. The public was barely aware it even existed. In 1968, Dyson wrote the obituary for Orion in Science, where he stated that this was the first time in modern history that major expansion of human technology has been suppressed for political reasons. Here, Dyson made public for the first time many of the details of Orion, its significance and lost promise. That same year, Dyson in Physics Today published his paper Interstellar Transport, where he outlined his plans for next generation Orion capable of reaching the star Alpha Centauri. This variation on the Super Orion abandoned using fission bombs in favor of a system using deuterium to create a pure fusion reaction. Is Orion really dead? The chances of setting up colonies on Mars using A-bomb ships would be politically impossible today, even if all the bugs were sorted out. The intervening decades have also unveiled new problems, including the effects of a bomb's electromagnetic pulses on unshielded satellites and the danger of heavy ions from the bombs getting trapped in the Van Allen belt. Then there is the problem of the bombs themselves. A whole new infrastructure would be needed to construct the bombs and to mass produce them in enormous numbers. Then there is the fact that these small bombs using minimal fuel are exactly the design that terrorists and rogue states have been looking for all these years. But there is one role that Orion could still fulfill, and it may one day justify building such spacecraft. One of the unlikely but frightening threats that the Earth faces is that of a rogue asteroid on a collision course with our planet. Because of the size of Orion and its ability to build up huge amounts of kinetic energy, the impact of a single unmanned Orion could deflect a 14 million ton asteroid a week before impact, and do it fast enough that a second could be launched if it failed. In the case of larger asteroids, a small fleet could be kept at the ready. So it's been 60 years since the Orion project began in the wake of Sputnik. Today, it's seen as a bizarre dream. But this fantasy was very much a thing of reality that died more from politics than engineering. It is also one that may well play a key role in the future of the human race as it expands its horizons to the stars. I hope you enjoyed this video. I was very happy to discover this very interesting topic with you. While waiting for the next video, you can find me on social networks, Facebook, Instagram, Twitter, and of course, you can visit at any time our Spreadshirt shop. You will find all the links in the description below. Please like, share, subscribe, support Section 51. I'll be back really soon. Open your eyes, watch the sky. Live long and prosper.